Hey Ramblers, this video covers chapter 11.4 in our textbook and deals with the areas of kites and related figures. So we'll start out talking about what are some of the figures that are related to a kite. So we know that the formulas we develop in this section or in this video will apply to them as well. And then we'll take a look at where the formula comes from, and then we'll apply it to a couple problems in the tutorials. Good luck, I hope this helps, and thanks for watching. Suppose we were given a rhombus. How could we find the area of the rhombus if we knew that the diagonals measured 40 and 30? So I'm going to call diagonal 1 40 and diagonal 2 30. Now you'll recall from chapter 5 that the diagonals of rhombus are perpendicular bisectors of one each other. So I know that this is going to be, diagonal 1 is going to be broken up into two parts that are 20 each, and diagonal 2 will be two parts that are 15 each. Now, how would we go about finding the area? Well, why don't you take a try at it yourself and then come back to the video to figure out if you did it the same way I did. One way would be to treat the rhombus as a collection of four right triangles. So we would multiply 4 times our triangle area formula, and we would get a total of 600. Or you might recognize it as two larger triangles, which are not right, but that have altitudes of 15. It's no surprise that we get 600 again. Well, either one of these is a legitimate way of finding the area, but let's kind of generalize it in the video on how we can find the area of all kites. Okay, as that last example just pointed out, there are definitely ways we could deconstruct a formula for finding the area of kites and just treat it as 2 or even 4 triangles. But kites come up often enough that maybe it's worth figuring out a formula for their own. So let's take a look at where a formula might come from. Well, if we were to break up a kite into those two triangles, the triangle of EKI there and the triangle ETI, then the area of the whole kite would equal the sum of the areas of those two triangles. Well, the area of triangle EKI would be 1/2 EI times KFs. So EI would be the base and KS would be the height. Then we would add to it the area of triangle ETI. So that would be 1/2 EI again, plus the altitude ST. Of course, you'll recall that the diagonals of a kite are perpendicular. So one of the diagonals can serve as the altitude to both of these triangles. Now, if I do a little algebra and I factor out a 1/2 from both the terms and the common factor EI, I'm left with 1/2 EI times the sum of KS and ST. Well, from the figure, it should be pretty obvious that EI is one diagonal and KT is the sum of the other two. So I can have a simplified formula for the area of a kite as 1/2 D1 times D2. That's not too bad. That's pretty easy to remember. Now be very careful. Get that in your notes and make sure that you notice it's multiplication of the diagonals, not addition. Because as we just learned with trapezoid, this formula looks a little bit like the area of a trapezoid, but that of course is addition. So let's not confuse the two. Okay, but this is a video about the area of kites and related figures. So what other figures should we be considering? Well, let's go back to a flowchart we saw in chapter 5. You'll recall that all quadrilaterals could be categorized as parallelograms, kites, or trapezoids. And kites, if they had two consecutive congruent sides, could be characterized as rhombuses. And of course, squares were always rhombuses. So our area formula for kites is also going to work for rhombuses and squares. So let's make sure we get that in our notes. That the area of a kite is 1/2 D1 times D2. The area of a rhombus could also be considered 1/2 D1 D2, and the area of a square is 1/2 D1 D2. So at this point in your notes, on your area formula summary sheet that I suggest you keep, you should have two formulas for the area of a square. Base times height, and now you have 1/2 the product of the diagonals. Since a rhombus is also a parallelogram, we could use the parallelogram formula for area for a rhombus also. So that could be base times height. or just 1/2 the product of the diagonals. It all depends on the information you're given. Okay, Ramblers, please be keeping your notes up to date. Thanks for watching, and I hope this helped. Okay, so in this video, we saw a formula which applied to kites and to two figures that are closely related to kites, rhombuses and squares. So we saw that the area of a kite can be expressed as diagonal 1 times diagonal 2 over 2. And that same formula can be applied to the area of a rhombus, d1, d2 over 2, and a square, d1, d2 over 2. Now let's take a look at our summary sheet for all of the formulas and see how this thing's filling up. So as you can see, we've added the area of a right triangle, which has come up in the exercises as the area equals 1/2 leg 1 times leg 2. We've also added a formula that came up in the exercises, the area of a regular triangle. You could also express that as equilateral or equiangular. And that is area equals s squared root 3 over 4. But then in today's video, we covered the area of a kite, which of course, as I just said, is area equals d1 times d2 over 2. The area of a rhombus is that same formula. And then way back at the top, under the area of a square, I put the new formula, area equals d1 times d2 over 2. So you can see that for each of these figures, we're starting to get multiple formulas for finding area. And that's going to really be the key to success in this chapter. Okay, Ramblers, a couple of problems for you in the tutorials. I hope this helped. Thanks for watching. Okay, number 4 on page 529 is an example of finding the area of a kite using the new formulas. So I like to first write out my formula. You'll recall that the area of a kite is 1/2 the product of the diagonals. Well, you also recall that the diagonals of a kite meet at right angles, and that the shorter diagonal is bisected by the larger diagonal. So I can see that if 1/2 of the diagonal is 8, then this lower part of the diagonal is also going to be 8. So my diagonal 1 is 16 units long. In order to find diagonal 2, I'm going to have to solve these right triangles. So the triangle on the left is clearly, knowing my triples, going to be a 6, 8, 10 triangle, and the triangle on the right is going to be an 8, 15, 17. So adding 6 and 15, I see that my second diagonal is 21. Then I just multiply to get the area of the kite. That product, of course, is 168. Okay, let's take a look at number 5 also, because it's just a good example of how these two, or how more than one formula can apply to the same type of a figure. Okay, if you look at part A, you can see that we're trying to find the area of this rhombus, which we can use the area of a kite formula for, because a rhombus is a kite. Since I know that one of the diagonals is 14, I can find the other diagonal by recognizing that when the 14 is bisected, I get a right triangle that has 7 as one leg, 25 as the hypotenuse, so the other leg must be 24, which makes the entire diagonal 48. So when I multiply these two out, I get 336. Now in part B, I could use the 1/2 diagonal 1, diagonal 2 again, but that could mean a lot of work. For here, it's much easier to just use base times height, because after all, a rhombus is a parallelogram. So I'm going to use 25 as my base, and my height is 20. So 25 times 20 equals 500. Okay, so it's really important that you know both formulas for for rhombuses and for squares, again, based upon the given information. All right, let's take a look at one more problem. That's number 7. That usually gives students trouble in this section. All right, number 7, they give us one diagonal, it's 13. So I'm going to use the 1/2 d1 times d2 formula, and I'll plug in 13 for diagonal 1. But I need to find diagonal 2. Okay, recalling that we have a right angle where the diagonals meet, if I look at just the upper half of the kite, and this is a right triangle, because although not all kites meet at right angles, the two sides do in this one. And so I can use the altitude to the hypotenuse theorems. So I'm going to say that h is going to be the upper half of this diagonal. And so h squared equals 4 times 9. Solving for h, I see that h equals 6. So since the shorter diagonal is bisected, I'll know that the longer diagonal must be 2 times h, or 12. So my area is going to equal 1/2 13 times 12, or 78. Okay, Ramblers, thanks for watching.